Welcome to a brand new episode of Machine Learning Made Simple. Here we unravel the enchantment behind machine learning, demystifying all the technical jargon. I'm your host, Shogato, and I'm here to chat with you about the revolutionary changes unfolding right before our eyes in the tech world. Let's dive in. Hey everyone, welcome back to another episode of Machine Learning Made Simple. This is our new season in 2025. Looking back from 2024, we are seeing now two clear trends developing in the tech world. One is robotics and the other one is agentic frameworks. Agentic framework is where the software programmatic improvements are happening, and then the robotics is where all those other improvements, hardware and machines and algorithms are coming together. So we're gonna take time to talk about both of those developments as we move forward. And also there is quantum computing, which is in a very nascent stage, so we're not going to touch on it right now, but we will revisit that topic as the field becomes more mature. But for now, we'll start with robotics and we'll talk about all the software that powers those robotics, and most of the software that powers the robotics comes from reinforcement learning. And now we need to understand how all these robotics are going to affect us, because these robots will soon be in our home, and I'll not be surprised, or you'll not be surprised if you bring home a robot with you to help with daily chores in like a few years, just like a car, and start making payments like a car payment. In fact, some of these robots would be the Optimus 2 brand robots would be around $20,000 US. So they will be pretty cheap, and most people will be able to afford them, especially with a payment plan. And I'm pretty sure Tesla will give out generous payment plans. The same thing they did with those Tesla Model Ys. I'm pretty sure Tesla is going to incentivize people to buy these robots, and they're ramping up the production. And soon in 2027 or 2028, you will see a massive flux of these robots coming out, and many people, definitely early enthusiasts, will start dipping their toes in and bringing home these robots. So it's important to understand what powers these robots. For now, some of these robots we can see from their demos are powered by ChatGPT, but what powers their machinery? What kind of algorithms helps these robots to navigate the environment? You see all these self-driving cars. What helps these self-driving cars navigate the environment, and how do they make these decisions? And this is crucial. We need to know what motivates these robots to make the decisions. What are the algorithms that powers the decision-making capabilities of these autonomous agents? These autonomous agents which can move around, and which is quite interesting and scary at the same time, because these agents can physically move around and make autonomous decisions. So we have to be careful and also understand and appreciate how these systems are learning and improving their models of the environments. So, and to start with, we'll delve into something, the next stage of reinforcement learning. So we already talked about the reinforcement learning, the basics, the how we can navigate a maze, like solve a game like Pac-Man. Now we are going to go to a the next level of complexity, which is not solving grid-like world problems, which are quite simplistic but also difficult for the early computer programs to solve. Now we'll elevate ourselves to solve games, the games that we used to play as a child in the early 80s and 90s, late 80s and early 90s, the Atari game that we used to play on a console, or sometimes I also even played on a computer, because they have a computer portable. Some of them were ported to the personal computer. We can also play them on computers. The next stage of evolution of the reinforcement learning was to solve these games just by looking at this, and this became big news in 2013, 14 and 15. You probably have heard it during that time, that AlphaGo and all those programs which are beating human beings in games and finding novel ways to play those arcade games. And this is where all it started, and that's the journey we're going to take. We're going to talk about how we can teach a reinforcement learning agent, an autonomous agent, to play those Atari games, like almost have human level comprehensions. And where does the human level comprehension comes in? Where the game solver or the autonomous agent can look at the game, literally look at the game using convolutional neural networks, and identify what's going on the screen, and then actually learn how to play it. and not only play it and play better than human beings, and now they can actually beat human beings hands down. But how do we do it? So it all started with this revolutionary paper that came out. It's called Playing Atari with Deep Reinforcement Learning. So where does the deep reinforcement learning come on? The reinforcement learning till now, till 2013, was pure code, where it just tried to solve the environment using some iterative process known as value iterations. And there are off policy and on policy methods. We talked about TD learning and all those things, but the main idea was perform iterations, okay? And it needed a grid of values to be given to it, and it can solve it. But this is next level. When we are talking solving Atari games are not grid-like system. They are continuous system. Balls are moving around, then space fighters are moving around. There are all kinds of stuff is happening. You have to look at the screen and see and understand where the ball is, or where the plane is, where the fighter plane is, and all those things you have to understand. I mean, by you meaning the autonomous agent needs to understand all those things in order to solve the problem. So that is a very, very complex problem. And even before we begin, let's talk about how complex the problem is and what we're really trying to solve here. So let's start talking about why do researchers love use Q-learning, and why is Q-learning so important, and what's the big deal? To understand that, let's first talk about its older cousin, value iteration. We covered this topic back in episode 47. If you need a refresher, please go back and check it out. Let's start with a fun example. Think of Pac-Man. And you've got this maze with food pellets giving you points, and then there are scary ghosts that can kill the Pac-Man if they catch the Pac-Man. So what the Pac-Man does, it goes around and eats those food pellets and gathers more and more rewards. But if they touch a ghost, it's game over. That's a huge negative reward. So value iteration solves these kind of problem in a pretty cool way. So how does it work? Let's take this simplified version of the Pac-Man. So how does the value iteration work? So let's talk about the maze, the Pac-Man maze. Let's take a simple setup. Let's say the maze is set up so that there is a large reward, let's say +10 for exiting the maze. So we have to, your Pac-Man has to navigate the maze, find all the food pellets, eat as many as can while avoiding the ghosts, and then exit the maze. And then there is a large negative reward somewhere, -10 for example. If it encounters a ghost, it's pretty much game over. And then there are food pellets scattered. Let's say there's a food pellet right next to a ghost. So you have to eat the food pellet and then run towards the exit. So how it's going to do that? So let's say we have a very simple grid system, and we set up this system with a large negative reward, let's say -10 in one corner of the maze and +10 in another corner of the maze, and there are like few small food pellets rewards of 1 scattered around. Okay, so now we perform something known as the value iteration using a formula called the Bellman equation. So what the Bellman equation says essentially is that if the Pac-Man picks up a reward, okay, then the value of the state in which it goes and picks the reward up, let's say it's cell 3, it picks up a reward, the value of the cell goes up because it found a reward there. And not only that, the value of the cells around it also goes up. So if I am on cell number 2 and I know I'm going to get a reward in cell number 3, then the value of cell 2 is going to be updated by the value of cell 3. But so if the value of cell 3 is 1, because it is going to get a food pellet of worth 1 reward point, then the value of cell 2 would be slightly less than 1, let's say 0.6 or 0.7. It is some variation. We have flexibility in choosing how much we are going to scale up and down, right? And then value of cell 1 would be a fraction of that. Instead of 0.7, let's say 0.4. Okay, so some fraction. Okay, so as we go further and further away from the cell which contains the reward, each cell will have diminishing rewards and it will have less values. The same idea. So, and if we keep doing this, essentially this is value iteration. Let's say cell 3 has a reward, then cell 2 gets a little bit extra reward like 0.7, cell 1 is 0.4. Similarly, cell 4 would be let's say 7 again. But it turns out if there is another reward in cell 6, then all these cells before through which the Pac-Man can go, all of their values will go up again. Okay, as more and more reward is concentrated, you can get the idea. So in the vicinity of rewards, all the cells will have really high value, and in the vicinity of a large negative rewards, all the cells will have a large negative value. So you see where this is going. The Pac-Man will now see where the issue is. Okay, so think of it like blue paint spreading out from reward cells, which is the pellets, and the red paint spreading out from penalty cells, right? The ghost. Over time, nearby cells take on a gradient of positive blue color or a negative red color based on their proximity to rewards or penalties. Now, after enough iterations, these gradients create a flux, and there are clear pads that are tinged. Sometimes these pads would be tinged blue because all of them are have high reward value, and some of them have high negative value, and they will be tinged red. So now Pac-Man will learn to follow the blue pads and avoid the negative pads, which it will lead to penalties, like leads to ghosts. But here's things can get tricky. Value iteration is great for simple grid-like environments like this, like our Pac-Man example, but sometimes it's not static. It needs the whole system to be static. If the ghosts are moving around, if the negative reward cell is moving around, then things become very hard, because with each iteration, we're not learning new things. We're seeing new scenarios come up, and the system is not going to learn very well. So things will get complicated pretty fast. So value iteration is very useful for simple state spaces where the state space is finite and it's static and it can be explored in a finite amount of time. But if the state space is constantly changing, is variable, and the state space, in some cases like the Atari games, where the state space becomes almost infinite, then it becomes almost impossible to use value iteration to solve these situations. So now let's consider a game like Pong. Let's say you are playing against an opponent with two paddles and a ball that bounces back and forth. Our job is to keep the ball from escaping using the paddle. The ball speeds up with every bounce, making the environment much more dynamic and complex. Suddenly, the value iteration will start to fail. So essentially, in Pong, you have to use the paddle to keep the ball in. Now, there are several complications. One of the main complications is that if we take a screenshot, which the system will learn by taking screenshots, each screenshot only gives the location of the paddles and that specific location of the ball at the time on the screen. Now that's all okay, but then the system is not going to know in which direction the ball is moving. If we take a screenshot, a single frame of the game, then the system doesn't, the reinforcement learning, the autonomous system which is learning how to solve the game, is not going to be able to know in which direction the ball is moving and how fast. So in order to do that, we need to take a series of frames. Let's say it's customary to take 4 consecutive frames, and then from 4 consecutive frames, the autonomous agent can figure out, okay, the ball is moving in towards left or right. It can figure out the direction and also with how fast the ball is moving. But now imagine how much memory and complexity this will consume. So let's taking this Atari game Pong. If we just freeze a single frame, which is 210 by 160 pixel, and if it has 128 color palettes, which means each pixel can take on 128 different colors, then the total number of possible screens would be 128 to the power of 210 times 160, which is a huge number. So those are the possible number of frames that the game can possibly have. Not all of them are not useful, but that's the state space. So all of those are possible state. Every pixel value for all possible combinations of the pixels, that's a state, that's a frame. Now that number is a huge, and it's practically impossible to analyze efficiently by any computer. It will take billions of years even for a supercomputer to solve this game if it's looking at the entire state space. The state space is almost infinite for all practical purposes, but most of these frames will never occur during gameplay. So this state space scenario is similar to a diffusion process. And why do I say that? Let's say some paint is dissolving in water. When the paint hits the water, it will slowly start spreading out across the entire volume of the water, and you see that direction in which it goes. It spreads, okay? It doesn't goes and collapses back from where it started. And the reason is that because entropy only increases. Or is that so? Entropy can also decrease, but those states are so less that we don't really see those states. We don't see the process where it starts from a spread out state, a uniform distribution of blue ink, which goes back into a single concentrated dot from which it started. And we know from experience that doesn't happen. Let's take another example. You see a glass fall on the ground and shatter. We don't see anything the other way, where broken pieces of glass mend themselves and become whole again, just like we say that in Harry Potter. We don't see that because that's not how the world works. But technically asking, can it happen? Yes, there is a state in the state space where the broken pieces of glass come together and mend itself and forms a whole glass again, whole piece of vase or glass or whatever the glass thing was made of. It becomes whole again. Those states are technically possible, but there are only like 3 or 4 such states compared to billions of other states where the glass just shatters. So even though they're technically, theoretically probable states where the glass pieces mend themselves into a whole glass, but compared to the millions of other states that are possible, observing those states become almost impractical, almost impossible, almost improbable, because they are like million, billion to 1, right? So we have to wait an entire age of universe just to observe that one event where broken pieces of glass will mend itself. So those states usually don't occur in nature. So it's the same thing here. So there are many states in the state space. Not all states occur with equal probability. So those are very low probability states, and that's the whole idea. So these Atari games, when we see all those possible screens, so there are like millions and billions of possible states that Atari game can take. Now all of those states, all of those frames will never be observed. But if we use value iteration, guess what? It's going to parse through, it has to parse through every possible state in the state space, and it will get stuck. It will take millions and billions of years to compute if you use value iteration. So value iteration is a no-go. So next possible option is the Q-learning, and that's why Q-learning became so important, because Q-learning can solve these problems of massive state spaces, almost infinite state spaces, without breaking a sweat. It doesn't need to go through all possible states. It just needed to sample a few, and then it's done. Now these researchers went ahead and did a little bit more optimization, where they said, okay, so now we are going to solve this problem, and we know that we don't need to see all frames. But the problem is that if we sample only a few frames, because if we have to sample 4 consecutive frames to know the direction of the ball, but other than it, if we keep sampling from same episodes, right? If I'm playing a game of Pong and then we sample only that episode, then we are only sampling consecutive events, right? So now each consecutive events, we can predict what will happen. It's like watching a game that we are practically memorizing. We're practically memorizing a chess game, all right? But the next time we play the chess game, the exact setup will not replicate. So now what? So essentially, when we are training a system, but just by looking at a finite set of moves or finite set of frames in this case, then we are overtraining the system, and the system is only going to be trained into that specific sequence of events. If those sequence of events repeat, then yes, it can play the game very well. It's not going to be robust against variations of those frames or variations of those sequence of events. So in order to make it more robust, now we need to have an IID distribution from which we sample, because of course, if we keep sampling consecutive moves from an episode of a game, then we are overtraining. We are only learning that game and nothing else. So we need to have a set of samples which are IID, independent and identical distribution. So in order to do that, we will sample from multiple episodes and pool all those episodes and randomly mix them around, and then we can sample randomly. Like we at least will keep 4 frames together so that we can see the direction in which the ball is moving. But so let's say we sample 4 frames from one game and four frames from another game, and then we can see how the paddle is moving, like the game is being played by a human player, and then we're learning from that. By we, I mean the autonomous agent. We're learning from that. Okay, so we need to sample a little bit more than 4 frames. Just make sure that they're not too much in a row, too many frames in a row, otherwise it will break the independent and identically distribution requirement. So this is what we're going to do. We can sample from different games. Let's say we have 100 games, and from each game we take a small short snippet, let's say 20-30 frames, and then we sample them. And then when we sample from 4 consecutive events from, let's say, episode 1, then 4 consecutive events from, let's say, episode 3, and that becomes IID over time. Create this repository, and this repository is known as replay buffer, and these researchers call them replay memory, but nowadays it's known as replay buffer. So the replay buffer can be, let's say, 100,000 examples or 100,000 frames from which we can sample, and that becomes full at some point after training. And then after we finish our training, then we can use those iteration method that we use for value iteration. Now we can use it for Q learning. We can iteratively improve the Q values by sampling from this. Let's say we sample, let's say the ball is moving towards right and the right paddle is moving up to intercept it. So that's a set of frames that we are feeding onto the autonomous agent, which is learning. And then we're going to feed something more. Let's say now the ball is moving towards left, and each time it sees something similar and figures out, okay, we have to do this next, we have to do this next. So now all this is well and good, but its state space is still too big. The state space is still too big because the number of pixel values are a lot. There are a lot of pixel values, and we might think, okay, that's not many pixels, that's very low resolution. The Atari games are like 210 by 160 pixels. That's nothing. We have like 2000 by 2000 pixel games nowadays, like full 3D. Yes, we understand, but for a reinforcement learning agent, the phase space becomes almost infinite, even if we increase the number of pixels by little. And that's interesting because we talk about self-driving cars, and these self-driving cars are learning how to navigate their environment, and their hardware is severely limited in navigating and ingesting all the information that's coming from the environment, because it can only see up to a certain resolution. Beyond that, the hardware that the self-driving cars have would not be able to analyze that data. And we think, okay, these self-driving cars are great. They are not that great. They are very, very, very limited. They have extremely tiny memory. Think about bees. These self-driving cars are like autonomous bees. Yes, they can move around and navigate the environment, but they're like, their brain's tiny. They don't have enough capacity to analyze their environment successfully, and that makes them kind of scary to be around. Then there are other people who think otherwise. That's an ongoing debate, and I don't want to get into that. So the whole point is, this reinforcement learning system, they have a limited hardware budget, and each hardware capabilities can analyze data up to a certain level. It can analyze the state space up to a certain level, and that's what we are talking about. How much can it analyze? Now we can simplify and make the algorithm more efficient by saying that, okay, we don't need to analyze the entire frame. The entire frame is like 210 by 160. That's too much information. Most of it is vacant anyways. We literally need only the location of the paddles and the location and the direction and the speed at which the ball is moving. That's all the information we need. But now we have an entire screen full of pixel values, that the extra information we do not need. We can of course crop it out, but that's a very inefficient method of doing it. A better method of doing it would be, as you might have guessed it, use a latent representation. Take the whole thing and dump it into latent representation. If most of the information is useless, then we can essentially dimensionally reduce this entire frame and compress it into very, very tiny latent representation, maybe like 10 or 20 bytes, and that's it. We don't need any more information than that. It's the same thing that's done in UNet or any kind of variational autoencoder. We take an image and encode all the information into a small latent space. So if there's like vast swatches of similar color, like the black background in a Pong game, all that color is going to be dumped into a single pixel value, and the information about the paddles is going to be dumped into maybe another single pixel value, and the location would be another set of floating point values that it will be encoded. If we are encoding by brute force the entire frame, it will take 36,000 floating point values to store it. But if we compress that into a latent encoding, it will probably take, let's say, 10 or 16 at most to encode the information of the entire frame. So that's probably a 10,000 fold decrease in memory optimization. That's a tremendous increase in efficiency, and that's where the DQNs are coming in. DQN stands for deep queue networks. So far, this not only these authors have introduced the replay buffers from which we can sample frames, which solves the requirement of markup processes that it needs to be identically distributed. They also introduced this idea that we need to compress the information in the frames because there's too much information. We don't need that many information. So compress that state space into a much smaller state space, and that really improves the whole idea, the whole process, because now we don't need to use all those extra information in the images. We can encode those images. And how are we going to encode the images? We're going to encode the images, and you guessed it, using convolutional neural networks, because there's the best way to encode those images. If we want to have a latent representation, it's not just one convolution network. We need to have like 2 or 3 layers of convolution neural networks, each successively reducing the size of the image and making them more and more compressed and getting a better latent representation. So in order to do that, we need 4 or 5 layers of this convolution neural network, and hence the name deep neural network, deep Q learning neural network, or DQN. And these DQNs were all the rage in the 2010s because they are now able to successfully solve these problems which were almost impossible to solve, computationally impossible to solve, because the state space was so big. So essentially they reduced the state space to a tiny amount using the DQNs, and now they can effectively solve this. Run it through a DQN, get the latent representation, learn on the latent representation iteratively, and solve it. So this a very vast reinforcement learning problem where it has to sample the entire space is now reduced to a very simple reinforcement learning problem which only has to iterate through a few loops of training, and that is it. So this is a major breakthrough, but there are still some issues that they didn't address then because they are still getting started, and that's what we're going to talk about next. The deep Q networks, DQNs for short, were able to completely solve these Atari games, and they did that by using the convolution neural networks to reduce the state space to a very tiny small amount. So initially the whole system was analyzing the entire frames, which each frame took up about like 300,000 for each frame, and like there will be thousands and thousands of those frames. So the state space was huge, but just by taking those state spaces and using convolution neural networks to compress those images into their latent representation, reduce those 3000 bits to, let's say, 4, 5 or maybe 8 bits, and then that substantially reduces the memory overhead and also the state space that it needs to explore. Now, once these are trained, initially if you look at an online video of the DQN training on the Pong, for example, then you'll see initially when the training just starts, then it gathers the points slowly, even though some of those videos are kind of sped up. So initially you will not be able to see the paddle move, but it is moving. What you need to more notice is how fast the points are changing. The initial training epochs, the points change very slowly, which means it's just acting randomly. The reinforcement learning agent is acting randomly. It's not really racking up any points. But as the training progresses over 100,000 epochs, then at the very end of the epoch, you will see the points are racking up very fast, almost extremely fast, that it's more than humanly possible. So that's when you know that the training is complete. Now, these deep Q networks, DQNs, and how do they solve the problem? We actually didn't talk about the architecture, so let's just hint at the architecture and see what the shortcomings are, and then see what the improvements that were subsequently made to these networks, because these networks were still slow. They took a really long time to train. In fact, it was not possible to train these reinforcement learning agents on a consumer grade GPU or hardware. So what are the improvements that happened? But first, let's look at the architecture in general and see where the bottleneck is. So the main architecture is a stack of 3 convolution neural networks. So initially, the initial convolution network has 8 by 8 filters. So filters is essentially what extracts those different image elements or features of the elements. For example, we talked about Haar filters, which is essentially a horizontal stripe, white stripe on a black background. And if you slide it across a human face, then it will pick up the eyes. So that's one of the features it can pick up. Then if you have a vertical bar, which will pick up the nose. So using the combination of these 2 filters, you can identify faces in an image. So you just go across blocks of image and then put your filter everywhere. Wherever the filter gives a non-zero value, like those horizontal filter will give a non-zero value wherever there is a set of eyes, human eyes, and then you match it, but there might not be human eyes, then it might be eyes of a frog, for example. Then you match it up with the vertical filter with itself, then it will identify the nose with the eyes, then you'll know, okay, it's not a frog, it's a human face, and then it will extract that information from that image. And you can do it iteratively over the entire image by scanning across each horizontal row. The same idea with convolutional filters. So essentially you can define any filters, it will randomly generate some of the filters and detect different features that are present in the diagram. That substantially reduces the memory overhead, because essentially you're extracting features, you're not extracting the pixel information, and the features are stored. And then the next layer, there will be more information, will be more higher level information will be extracted from the features. For example, if let's say the first layer will only detect edges, right? And then there's another filter which will detect contrast. Now the next layer might include those edges. So is it a rounded edge? It will combine those multiple rounded edges, and then it will learn to detect a circle. And then the next higher level convolution neural network will be able to combine those circles to form broad range features, like 2 circles might form eyes, for example. And then it will learn as we add more and more convolution neural network, each one will learn a higher level information. So for these deep Q networks, only 3 layers of convolution networks are sufficient to learn all the features, all the lower level and the higher level features. And so that's what the researchers have used. And once all the features are extracted, then they are dimensionally dumped into a single layer of, it's a linear layer. They dump it in essentially they flatten all the representation. So initially the image was 210 by 160 pixels. So, and as each iteration of convolution neural network will reduce the resolution bit by bit. So maybe it is reduced 4 times, first 50 by 40 in the next layer, and then it gets halved, becomes 1/4 of that size again. But now we have enough latent representation that we can flatten it. So they flatten that into a linear layer, and then once we flatten that linear layer, if you remember your neural network architectures, it's easy to feed that flattened network to a loss function. And essentially it's now a layer, it's a single layer of values. So let's say there are 512 units in the final neural network flat layer, linear layer. It will take all those 512 values, so those are 512 floating point values, and that becomes a single vector, and that can be directly fed into a loss function, and the loss can be calculated, and then stochastic gradient optimization can be performed, and then all the losses can be back propagated through the network, and then the system can quickly learn to go to the minima. Essentially so this is slightly more complicated because the loss function also include the Q learning itself. So now that we have these vectors, the loss function can be pretty straightforwardly calculated, because we are using the RL network to predict something, right? So during the training phase, let's say we are about to hit the paddle, then we move the paddle upwards, right? And then we feed that into the system and the environment in the OpenAI gym in which it's running. Then the environment gives feedback that, okay, you moved it upwards, and it turns out that you missed the ball, it went below you. So you should have really brought the paddle down instead of moving it upwards. So our action is moving upwards, but the expected action is moving it downwards. So you can calculate the loss. So now moving it downwards has its own frame. So you sample that frame of the paddle moving downwards, push it through the DQN, get its vector representation, the 500 unit vector representation, and now your RL agent's prediction was moving it upwards. Then that frame has its own vector. So now you compare those vectors and see what is the loss, and then you back propagate that loss. It's the same thing as we do for training a regular neural network. So once we have formalized this vectorization process, taking a frame and converting that to a 512 dimensional vector, then we can essentially anything. Now we can take any frame and convert it into a corresponding vector, 512 dimensional vector, and we can now perform loss, gradient descent, and we can do any kind of stochastic gradient descent using any kind of optimizer. You can use Adam optimizer. So the rest remains the same. The only part was using the convolution network to convert those frames to a vector value function. So now it turns out that all this is great, but since there is a slight lag in the response, because when we move the paddle, we have to anticipate the ball is coming towards us. So only when we move the paddle for a substantial distance that we actually get the reward, that we are able to successfully intercept the ball and prevent it from going out of bounds. Since our rewards are slightly delayed, and we have to sample a little bit more from the future values of Q, and that causes a little bit of stacking up of the Q values. So it results in overestimation of Q values. RL agent needs to be optimistic in any action it takes. I mean, that's the intuitive way of looking at it. So the researchers noticed that anytime these kind of systems were trained, the system becomes slightly over optimistic. They overestimate the Q values, and mostly because of this, because they need to be optimistic that we have to go there, and then you will feel it's like it's ancient encoded in our genes. Like, we have to be optimistic about doing something, otherwise if we think that we're going to fail, then we're not going to do it, right? So most human beings has an optimism bias. Most human beings can do things because they know that they'll get a future reward in return, and so they do those things even though the rewards are not immediate. Now there are variations of this. Some humans, so this is known as a discounting factor. Most humans do discount the future rewards, but some human beings discount it more heavily than others, and it changes for even a same human being. The discounting factor changes over their lifetime. As a student, they might have a higher discounting than when they acquire substantial wealth. For example, let's say a simple example that Daniel Kahneman and Amos Tversky performed with student population at different universities, Ivy League schools, is that they offered them money. They're like, okay, I can give you $100 now, or I can give you $150 1 year from now. Right? So most people, you can tell that they're going to choose the $100 now. No one is going to wait for $150 for a year. Now, if the equation changes, just change the amount from $100 to $1,000. Let's like, I can give you $1,000 now, or I can give you $1,500 a year from now. The ratio remains exactly the same. The rate of return is 50% for both the cases. And guess what? In the second version, most people will opt to wait 1 year. Most people will rather wait 1 year and get that extra $500. So people are discounting the monetary values differently based on the absolute value of the money. For when it's $150, no one wants to wait 1 year for that extra $50. But when it's that extra $500, people are willing to wait 1 year to get that extra $500. So this is different. So these are called anomalies. And this is a part of behavioral economics, where people behave differently based on different absolute amounts or values of any kind of fungible asset like money. So there is another bizarre phenomenon, and which also applies to this discounting factor, was like, if we ask someone, let's say someone who is well established and for whom there's little difference between $100 and $150, someone who has substantial wealth, if you ask them the same question, they would wait 1 year to get that $150, because they don't care about waiting. For them, getting the $100 today or $150 a year are kind of equivalent, so they are willing to wait. So what we say is that those people who are willing to wait 1 year, they have very low discounting factor, which means for them $100 now and $150 now have kind of the same value than from 1 year from now, compared to the people who are not willing to wait 1 year to get that $100. They want the money now. So which means their $150 a year from now has has very little value to them right now. So $100, if someone is preferring $100 today over $150 1 year from now, they are saying $150 1 year from today is worth less than $100 present time right now. So their discounting is more than 50% for a year. So they have a very high discounting rate, and people who are willing to wait 1 year to get that extra $50, they have a discounting rate which is less than the rate of return, which is the 50%. So if my rate of discounting is less than rate of return, I will wait for those interest rates to accrue. So that is why some people do not like investing in certificate of deposits or any kind of fixed deposit which gives a very low fixed rate of return, let's say 3 or 4%. They don't like it because their discounting rate is very high. Some people's discounting rate is like 10 or 20%. They would not want to store money in those savings account. Either they will go store it in a very high return mutual fund or actively managed mutual fund or very high risky stock. Maybe they'll buy Tesla, or they'll just gamble because they have very high discounting rate. So these are part of our behavioral economics. This discounting rate exists in every human being, and the reason because we expect future returns. So the same thing with deep Q neural networks, the discounting rate, if you look at the Bellman equation, is already included. But in spite of the discounting rate, the future rate of return must be accumulated in a certain way so that the autonomous agent can feel that it is worthwhile going in this direction. It's worthwhile going up in order to intercept the ball. It's worthwhile going down in order to intercept the ball. So any action any reinforcement learning agent takes, it is predicated on the fact that it will get some kind of a future return, which is of course discounted to the future by a certain discounting rate that the researcher decides. Discounting rate can be high or discounting rate can be low, but more often than not, these discounted rewards accumulate over time and causing a high Q value, because otherwise the RL agent is not going to move. It's not going to take an action. It needs to be compelled to take an action, and that's where the high Q values come in, which is all well and good, but it needs to be brought in line. That's where there is a variation of this DQN model, which is called a double DQN model. And the double DQN model, what it does, it maintains two separate Q networks which are identical, but it does not update one and updates one. So it updates, let's say, trains one neural network, and then every once in a while copies those values to the other network, the target network, and just keeps it as it is so that the Q values doesn't go too high in one of those. So how do we solve this problem of over-optimism of the deep Q networks? So one of the seminal papers which discusses this is the paper by Hasselt et al. It is called the Deep Reinforcement Learning with Double Q Learning. So their novel idea is that, so they acknowledge that the fact that there is optimism in part of these deep Q learning, reinforcement learning agents. They become over optimistic, and of course they should be, otherwise they'll not take action. But a little bit of optimism is good, but too much optimism is not good. So the solution that was proposed in this paper was to maintain two DQNs, two deep Q neural networks. Let's say we have one, let's say network one, which is continuously training like the original DQN. And then there is network 2, which is mostly static, but every once in a while we update the Q values or the weights of the second network from the first network, but not always. Sporadically we'll update. But here's the trick: all Q values that are being updated in network 1, which is being continuously trained, is actually coming from network 2. Okay, so we have copy 1 and copy 2. Copy 1 is changing, but the values of copy 1 that are updating are actually values from copy 2. So the copy 2 is mostly stable. So let's say there are like 100 training episodes. For 100 training episodes, the Q values have remained same, and I'm updating the Q values on copy 1 using those Q values in copy 2. Okay, so which means it's the copy 2 is not changing, but copy 1 is updating. But since it's mostly grounded, so we don't see a massive spike or massive variation of the Q values, because they don't get out of hand very fast, because we are using the stable values which have been constant for, let's say, 100 epochs of training in copy 2. So once we have stacked up a little bit of extra q learning and learning values, and we know it has moved in slightly in one direction, then we can copy those values back to those copy 2 of the neural network, and then it gets slightly updated. So that keeps the whole training stable and move in a direction in a very stable manner without overestimating the q values. So essentially we are tying one network to another network and making sure that it doesn't deviate too far from the other network, right? So think of it like this. Let's say we are drawing a portrait and then we are letting our imagination fly, but every once in a while we are taking a picture and it's like, okay, this is what you're working with, don't deviate too much from that picture. So we'll draw somewhere around it, then we'll take a snapshot, and it's like we don't want to deviate too much from that. We are essentially checking our own work and making sure we don't deviate too much from the standard values that we have agreed on. So this technically works in practice, and there are some theoretical results which the authors show that it makes it more stable, but it's, frankly speaking, it's mostly empirical. The reason it works, the overestimation can be accounted for by understanding that overestimation has to be there. It needs to be over optimistic, otherwise the network is not going to perform well. But adding a separate standardized network to keep the first continuously training network in check is some kind of a regularization method that they have implemented, and that works well in practice. Alright, before we wrap this up, let's talk about one more game-changing idea in this area of DQNs, Deep Q Learning Networks. So this was a concept that was introduced in 2015-2016. It's called Prioritized Experience Replay. It's one of those ideas that makes you go, oh, of course, that makes so much sense. But it did take a ton of research and insights to get there. So here's the background. In the classic DQN setup, the replay buffer, we talked about replay buffer, it plays a crucial role in weighting and IID independent and in uniform and independently distributed distribution from which we sample. And the reason is this, there are correlation between consecutive transition in the gameplay. So imagine you're playing a game, most of the time the environment doesn't change drastically between one action and the next, right? It's pretty smooth from one frame to another. It's fairly smooth. But stochastic gradient descent, which is used to train the deep Q networks, the backbone of the deep learning algorithms, that one assumes that the training data from which it is sampled is independent and identically distributed, IIDs, which isn't true for the sequential frames that we are encountering during gameplay. So the original DQN, as we described before in this episode, they tackled this mismatch by creating a large replay buffer, let's say of 100,000 episodes, where it stores those transitions and then randomly samples for it. And then there is a little bit nuance there, because it cannot sample one frame, because if it samples one frame, that it just sees the image of a ball, it doesn't know in which direction the ball is moving or how fast it is moving. So if it just samples a single frame, it is what is known as a POMDP, partially observable MDP. A partially observable MDP is, as its name says, is partially observable. Let's say you're playing a game of poker, you know your hand, the cards that you have, you know the cards that are on the table, but you don't know what the opponents are holding, what cards they're holding. So that's a partially observable Markov decision system. So, but we cannot deal with POMDPs. They are quite complex to deal with. In fact, the most self-driving cars deal with that all the time. They are always dealing with partially observable systems, because they cannot see what's around the corner. They cannot see the big picture. So now you might say, okay, but human beings drive cars too. We don't see it on the corner. But guess what? We human beings can make models of the universe very successfully. We can see patterns, we can create entire distributions, we can see the flow of traffic. Okay, then we know, okay, there's something around the corner. If we see a traffic jam or traffic moving slightly differently in front of us, we can predict, okay, there's something going around the corner, I need to slow down. Okay, so we can build that model of the universe very quickly. We're very good pattern matches. In fact, that's why we also see all those animals in patterns in the stars, with Pisces and Libra and all those things in the stars. We also see patterns where it doesn't exist. And people say that's why religion exists, is because we started seeing patterns where there is no pattern. I'm not going to debate pro or against any of those ideas, but human beings are excellent in creating models in universe. In fact, that's one of the main thrusts that the reinforcement learning is trying to do. Instead of training the reinforcement learning agents to create the model of the actual universe, they are trying to create the probabilistic, to learn how to play the game. They're trying to make the RL agents to create that model of the universe so that they don't have to learn exactly the rules of the game. They can model the game, they can model the environment, and then they can learn to navigate in that model environment. So then essentially they are taking a partially observable universe, which is the gameplay, and then creating the entire universe out of it, which is a fully observable system. So that's a very advanced topic we're not going to touch upon right now, because partially observable MDPs are advanced topics. But the way the deep Q neural networks gets around that is by sampling 4 frames in 4 consecutive frames, and that way we know the ball is moving from, let's say, left to right or right to left, and in which direction we can predict the direction and the velocity and the speed with the ball is moving. So we sample 4 frames at once. So that's how the DQNs goes around that problem of the environment being partially observable. So it has to sample 4 frames. So when it samples from the replay buffer, this random sampling does introduce some independence into the training batches, and that helps with the assumption of the stochastic gradient descent, which assumes that all the samples are independently and randomly sampled. So although the random sampling introduced some independence into the training of the batches, so this paper, the Prior-Torres experience replay, asked an important question: why treat all samples equally? Shouldn't some transitions be more valuable to learn from the others? So to answer that, let's consider a motivating examples which the authors actually talked about in the paper. This is known as the blind Cliff-Walk problem. This an agent navigates a sequence of states where there is only one reward which rises at the very end. So let's say there are like 20,000 steps and there is one reward at the end. Now, what is the challenge? Because most transitions lead nowhere, because if we are using discounting, even a tiny amount of discounting, let's say if your discounting rate is 0.9, which is pretty low discounting rate actually. So even with such a small discount, so it will accumulate to a large value. So essentially 0.9 to the power 10,000 is like pretty much 0. So even there is a tiny reward at the end of 10,000 steps, guess what? I'm not seeing the reward. I'm seeing almost a 0 reward. So there is no incentive for the agent to move forward in order to get to the end of 10,000 steps to get the reward. So imagine trying to get a PhD, imagine trying to excel at some sport. So most of the time people don't see the end at the light of the tunnel, and people get demotivated because it's a long and arduous journey. If there is a reward at the end, if the PhD is completed successfully, if there is a research position open, if there is a spot in the NBA open after those long and arduous training routines that basketball player has to go through, even if there is a spot open, if there are like even more brilliant players, that genius prodigies come and take our spot after our like 10,000 hours of training, why would we waste so much time to get that tiny reward at the very end? So that demotivates people. And the same thing, a long training regimen, just like we described, also demotivates our reinforcement learning agent, because it doesn't see the reward come to it in the present state. So without guidance, the agent has no reason to keep exploring. It's like walking in the dark with no sense of where we are heading, whether we are heading in the right direction. Instead of randomly sampling from the replay buffer, the method focuses on the rare high-value transition. So for example, let's say in the blind Cliff-Walk problem, let's say we are an oracle and we only sample the last 10 steps. Then we can see, okay, so there is definitely a reward there. Okay, so here's the motivation. So since I sampled the last 10 steps, so my reward is not just almost 0, it's like, let's say 0.9 to the power 10. So it's not that high, but it's still there. So that gives some amount of motivation to move in that direction. So the same thing, the same idea of Prior-Torres replay buffers is that don't sample all the events, because some of those events we are just wasting time because it's not going anywhere. So this method really focuses on rare high value transitions, like those are the last few steps in the blind Cliff-Walk problem. So by prioritizing these transitions that really lead to high rewards, the agent gets a glimpse of what's possible and making it feel more motivated to take the necessary steps and start exploring, even when the success seems distant. It's like showing the agent the light at the end of the tunnel. So how does this work in practice? The idea is to assign priorities to each sample in the replay buffer based on how surprising or useful it is for training. Specifically, the priority is proportional to the training loss. So we take the training loss for each frame. So let's say we execute a set of actions, generate a set of frames, have corresponding vector representation from the DQN, and find its corresponding loss, and use that training loss to say, okay, these frames that we have sampled, these are its training losses. If the training loss is high, then the priority is probably low. If the training loss is low, then the priority is high. So then that's how we do on pre-training, by doing a set of training and then assigning these priorities to the replay buffer, and then chop off those frames that really are of low priority so that we don't sample them. So how much the agent learn from that sample? We just push it back into the replay buffer. So the rule of thumb is simple: train more on data that really surprises you. Of course, there is a tricky balance to maintain. If the agent focuses too much on a small set of high priority samples, it is risking overfitting and losing diversity of the experiences that is needed for robust learning. So to address this, the algorithm also combines prioritized sampling with random sampling, and it annihilates the bias, because it does create a bias towards prioritized sample by some kind of a weight, which they have some function that they define as the weight they multiply it with the prioritized samples, so that it gets normalized and the bias is removed. It's just like you did in statistics. You essentially multiply by a weight to debias your samples. So for example, it's a very simple example. If we have randomly sampled from even identically distributed population, we'll introduce bias. In that case, we'll take the sample size, let's say n, and then we take this original sample distribution variance and divide it by the square root of that sample size, and that will essentially debias the standard deviation. So that's one way of debiasing it. So the same idea here. So they use some function of that 1 over n. So instead of using 1 over square root of n, they use some 1 over n to the power some beta, where beta can take some value. They suggested 0.6. So instead of using 0.5, they use 0.6. So in standard deviation debiasing, we use 1 over n to the power 0.5. These people are using debiasing factor of 1 over n to the power 0.6. So now to avoid the bias from oversampling higher priority transitions, the method also uses importance sampling weights that like we described, and this ensures that the agent doesn't skew its learning too far in one direction. So in short, this prioritized experience replay makes learning smarter by focusing only on the transitions that matter the most, like a coach pointing out your biggest mistakes and helping you improve faster. In fact, that's known to be what best coaches do. They don't give too many instructions. They only fix minor mistakes and nudge in the right directions. So the best baseball coaches, the best football coaches do behave like that. They only point out those tiny mistakes, and those tiny improvements accumulate over time. So it's a simple yet profound change that has a huge impact on reinforcement learning. And it all started with the realization that not all experiences are created equal, just like life. Until next week, stay curious, stay critical, and keep asking those important questions. See you next week. That's a wrap for today's episode of Machine Learning Made Simple. If you have questions or want to explore AI topics further, please don't hesitate to leave a comment. Until next time, keep exploring and enjoy your AI adventure.